Last week we looked at volume, temperature, and pressure and how they affect the state changes in solid liquids and gases. Specifically, we studied the temperature and pressure changes through a phase diagram. This week we are going to kind of tunnel our focus in on gases because they have a unique quality called expansion and compression of a gas. And that just means that now their volume can also play a role in kind of their behavior. So we have 3 gas laws, is what we call them, but really they're just describing relationships between pressure, volume, and temperature variables. So the 3 gas laws are named after the 3 scientists who kind of discovered these relationships. And each of these laws keeps one of the variables constant while the others are changing. And we just have to keep in mind as we're talking about these that constant variables in real life don't really exist. They can exist in labs so that we can observe relationships, because we will intentionally keep one or another variable constant, meaning it just won't change from beginning to end. However, in real life, all 3 will change. So these laws individually will help us put together what's called the combined gas law and the ideal gas law, which we will talk about in the next 2 weeks. So before we get to that, let's talk about these individual gas laws. We have Boyle's law, Charles' law, and Gay-Lussac's law. So Boyle's law relates pressure and volume inversely. Inversely means opposite of one another. So the relationship will change opposite. If we have higher pressure, thinking about squeezing something, that will compress the volume and make it smaller. So we have an increase in pressure causes a decrease in volume. And the constant variable here will be temperature. So just like I said, if we increase the pressure and squeeze something, adding force, our volume will go down. So there's our inverse or opposite relationship happening. And the opposite is also true. If we decrease the pressure, maybe we, release off of squeezing on a balloon per se, then it will expand again. Our volume will go back up. To describe volume, generally when we're talking about it getting smaller or decrease of volume, we will say that it's compressing. And when the volume gets larger and it's an increase, we'll say it's expanding. So our graph here, if you have, let's put pressure on the y-axis and volume on the x-axis, we see when the pressure is high, the volume will be low, and then they will just kind of like a little curve there of how they're related. This is an inverse relationship. And we said this is called Boyle's law. The next one we have is Charles' law. And Charles' law relates volume and temperature. These 2 are directly related. So that means our pressure is constant here. And if you think about things that will expand and compress, that's referring to their volume, larger and smaller, based on seasonal changes. I think about my wood floors, how the particles in the wood, there's gas particles in there, and so during the winter it kind of compresses and the volume shrinks and there's little cracks in between my wood. If you have wood flooring, you've probably seen it do that. And then in the summer it gets hot, particles speed up, they start to expand, and suddenly my wood is back to no cracks. So we have this expanding and compressing of the volume based on changes in temperature. So our arrows are going to be going the same direction because they are directly related. That means, same. Inverse is opposite. temperature goes up, my volume expands. As my temperature goes down, my volume compresses. So if I put my variables here, temperature and volume, this time they're changing together. I don't know why it keeps making that little nugget at the top. Okay, there we go. So this is a direct relationship, and this one is Charles' law. Temperature and volume. The third one is Gay-Lussac's law, or sometimes I just call it GL law. And this one relates pressure and temperature. So that one has constant volume. And as we just saw with Charles' law, temperature is related to volume as well. So generally, if we're going to be changing temperature, it would also affect the volume in real world scenario. But for the case of just focusing on this individual relationship, we are saying that volume is going to be staying constant. And these two are also related directly. So that's also same. So this is going to look a whole lot like Charles' law. When temperature goes up, pressure goes up. When temperature goes down, pressure goes down. And an example of this, I think about my wedding ring. The force around my wedding ring and my finger is pretty low, so that'll be low pressure in the winter. So again, these seasonal changes, because the particles of gas in my finger are not pushing with as much force because they are not as excited from temperature, so they are kind of compressed. Well, compressed really describes the volume, so here we go, kind of seeing that overlap. But the force of those particles are pushing out onto my ring, causing higher pressure around it because of the lower temperature. And then in the, hold on, let me go back. Higher pressure caused by higher temperature in the summer, and lower pressure caused by lower temperature in the winter. So that is a similar relationship to Charles' law. If I have pressure, volume, now there's GL law, also a direct relationship. So if you can remember, the temperature ones are both direct relationships, and then the one that does not have temperature involved because it's constant is an inverse relationship. That helps me remember their relationships. One more note down here, we have pressure changes on Earth. This will be important for some of the questions that you were asked, because it'll tell you about kind of the altitude or being in the ocean or something like that, and that affects the pressure. So if you ever see altitude changes in a problem, it's referring to pressure changes. So just a note of clarification here, if we are, at ground level here, this would be atmospheric pressure. And as we go up into the air, up into the mountains we have drawn here, then our gas particles actually become less dense, and we have lower pressure higher up. So if you're in an airplane or you're hiking in the mountains, you will have lower pressure in the environment. And then as we go down into the ocean, we have more density of water particles packing around you, so this causes higher pressure the lower you go into the ocean. So lower pressure down, lower pressure high up in the air, and higher pressure down in the sea. So this will help you in working out problems that talk about kind of where you're at and location. Those are referring to pressure changes and can be used to relate to both volume. I labeled this one wrong. This should be temperature. Can be used to relate volume and temperature, since we have those pressure relationships here. Okay, so that's just to help you analyze pressure a little bit. So on our next page here, we have some examples of gas laws. So I want you to kind of think about them and use kind of the arrows like this to describe what's happening. Or you can literally write pressure increase, volume decrease, or whatever happens in the problem. But I want you to describe what's happening and then which gas law causes it. So a balloon is placed in a pressure chamber and the pressure increases. So we've got pressure goes up. What will happen to the volume of the balloon? So our pressure chamber is going to squeeze the balloon, increase the force around it. What should happen to the volume? Volume will go down. Which relationship or gas law causes this? This is the pressure-volume inverse relationship. That's Boyle's law. These are all pretty quick. I want you to do 2, 3, and 4, and then we will check them together on either Thursday or Friday when we're together. And then the other practice for today is Wilson's Adventures. So if you've seen Castaway the movie, this is the little volleyball friend that the main character creates while he's shipwrecked on an island. Actually, his plane crashed, and he's on an island trying to survive. So this is focusing on the little volleyball friend, Wilson. So here goes the story. While hanging out on a lonely, isolated island, Wilson started to get bored, so he decided to go on a few adventures. In each of the following situations, draw a picture of what happened to Wilson or the objects he encounters and describe what happened in words. I'm also going to be okay with arrows like we did on the previous page. This is a fair description, just showing me what's happening to the variables. Use terms like temperature, pressure, and volume to describe the situation, or you can use symbols PVT. And then color your pictures for extra credit. And there are, I believe, 10 questions. So let's start. We'll do a couple of these together. Actually, we'll probably just do one together, and then you can do the rest. So we've got Wilson was sitting in the hot sun trying to get a tan. He was beginning to feel very bloated from his volume, beginning to expand. So we have volume and we have hot sun. So that should give you the hint that we're going to be using the variables of temperature and volume. So hot sun is increasing temperature, and it says he's feeling very bloated. So that's an increase or expansion of our volume. So there's our key there, expanding. Our volume's increasing, hot sun is high temperature. So let's draw before and after, kind of before the sun. So there's little Wilson. I don't know how to draw him very well. There you go. You can look up a picture of Wilson if you'd like. And then we'll put him in the sun. And we'll make him expand. And the reason that the gas laws will work on Wilson is because he's a volleyball, so he has gas particles in his body, if you will, or his head. So as the temperature increases, the volume increases. And there's your cute little picture. You can add more detail if you'd like. You want to put him in, whatever. Put him on the island or just show the example of what's happening. Wilson started to feel a little hot, so there's another temperature reference, so he rolled into the ocean to cool off. This one doesn't really tell us what's going to happen, so we have to kind of figure that out ourselves. So he's feeling hot and he rolls into the ocean. So let's draw him feeling hot in the sun. Guess he should probably be just as big as he was in the first problem. Okay, so he rolls into the water to cool off. So to cool off, that tells us our temperature goes down. And then we know a couple of things that can happen when temperature goes down based on our relationships. So for this guy, he's going to go into the water, and now his volume is going to go down. And technically also his pressure would go down, because this does not clarify, if it's being held constant, because real world problems often don't keep it constant. So this is kind of a combo of Charles' law and GL law.